Most people think hacking starts with passwords, or viruses, or even IP addresses. But the real battlefield of computer network starts much lower than that, on something you use every single second without noticing, that is port numbers. Every time you open YouTube, send a message, or visit a website, your computer is silently choosing a door to talk through, and that door is a port. Now hear the scary part. If you don't understand how ports work, you don't really understand how data moves across the internet. In this video, we are going to break down port numbers in a way that finally makes sense and show you why they are the hidden backbone of networking and cybersecurity. Now that we understand the need for port numbers, let's look at what a port actually is. A port is a virtual communication point where network connection begin and end. Unlike physical ports on a computer, network ports exist in a software and are used to manage communication between devices and applications. Each port is associated with a specific process or service running on a device. When data arrives at a server or computer, the operating system needs a way to determine which application should receive that data. This is accomplished using port numbers. A port number is a numerical identifier assigned to a particular service or process. It helps the operating system forward incoming network messages to the correct application. For example, if multiple services are running on the same server, port number tells the server exactly which service the incoming data is intended for. In simple terms, while an IP address identifies the destination device, a port number identifies the specific service or process on that device that should handle the communication. This allows multiple network services to operate simultaneously on the same device while ensuring the data reaches the correct destination. Now, if you understand port numbers, let's understand what are its different types and how it is divided. Port numbers range from 0 to 65,535 and are divided into three categories. Well-known ports range from 0 to 1023 and are reserved for common network services. Registered port range from 1024 to 49151 and are assigned to specific applications or vendors. Dynamic or private ports range from 49152 to 65,535 and are typically used temporarily by client applications. While there are thousands of port numbers, you will frequently encounter a few common ones in everyday networking. Port 20 and 21 are used by the FTP for file transfers. Port 22 is used by the SSH for secure remote access. Port 25 is used by the SMTP for sending emails. Port 53 is used by DNS to translate domain names into IP addresses. Port 80 is used by HTTP, while port 443 is used by HTTPS for secure web communication. Now that we know what port numbers are and some common examples, let's see how they are actually used during network communication. Now let's understand some important concepts related to port addressing that you will often come across in networking. First, an open port. An open port is a port that is active and listening for incoming network requests. This means a service or application is running on that port and is ready to accept connections. Closely related to this is a listening port. A listening port is simply an open port where a specific service is waiting for incoming communication. For an example, a web server listens on port 80 and 443 for incoming web requests. On the other hand, a closed port is a port where no service is running. If a request is sent to a closed port, the system will reject it because nothing is listening on that port. Now let's look at port scanning. Port scanning is the process of checking multiple ports on a device or network to identify which ports are open, closed, or filtered. Network administrators use it for troubleshooting and security checks, while attackers may use it to find potential vulnerabilities. Next is port forwarding. Port forwarding is a technique used to allow external devices from the internet to access a specific service inside a private network. It works by directing incoming traffic on a specific port of a router to a particular device within the local network. For an example, you can forward request coming to a public IP on port 80 to a web server running inside your home network. Now another important concept is source port and destination port. When a device communicates over the network, each packet contains two key port values. The destination port identifies the service on the receiving device, while the source port is temporarily port assigned by the operating system to keep track of the response. For example, when you open a website, your computer might use a random source port like 52431 to connect to the destination port 443 on the web server. Understanding this concept is important because they explain how devices manage multiple connections, how data is controlled across networks, and how security and access control work in real-world networks. Understanding only the theory is not enough. Let's understand it using the practical demonstration. Now let's see the concept of open ports and closed ports in action. For this demonstration, we will use a tool called Nmap. Nmap stands for Network Mapper. It is a network security tool used to discover devices on a network and identify whether ports are open, closed, or filtered. Before we begin, let's install Nmap. First, update the package list by running sudo ft update. Once the update is complete, install Nmap using sudo ft install nmap. Now that Nmap is installed, let's find our IP address. To find that, run ipeditr. For this demonstration, we will use the loopback address, that is 127.0.0.1. Since both the client and the server are running on the same machine, this address allows us to communicate with ourselves. Now, our goal is to check whether port 8080 is open or closed. To scan a specific port using Nmap, type nmap-p 8080 127.0.0.1. Here, -p option tells Nmap which port to scan. As we can see, Nmap reports that port 8080 is closed. This means no application or service is currently listening on that port. When Nmap attempts to connect, the operating system responds that the port is unavailable. Now let's open the port by starting a simple web server. Run the following command: python 3 -m http.server 8080. This starts a Python HTTP server and makes it listen on port 8080. Notice that the terminal is now waiting for incoming connections. This means the service is actively listening on port 8080. Let's open a second terminal and run the scan again. Nmap-p 8080 127.0.0.1. This time, Nmap reports that port 8080 is open. The port is now open because an application is actively listening and ready to accept connections. Finally, let's stop the web server by pressing Ctrl+C. Once the server stops, scan the port again. As expected, Nmap now reports the port are closed. This demonstrates a very important concept in networking. A port is considered open only when a service is actively listening on it. When that service stops, the port closes and can no longer accept incoming connections. Now let's visualize the listening process and see what it means for a port to be listening. For this, we will use the ss command. Type ss-tuln. This command displays the network socket currently active on your system. It is one of the most useful commands for checking which ports are open, which ports are listening for incoming connections. Here SS stands for socket statistics. The option -tuln tell the command to display TCP and UDP listening sockets in a numeric format. Let's execute the command. As we can see, there is currently no entry for port 8080. This means that no application is listening on that port. Now let's start a simple web server by running python 3 -m http.server 8080. This command starts a Python HTTP server and instructs it to listen on port 8080. With the server running, let's open another terminal and execute the command again. ss-tuln. Notice that port 8080 now appears in the output. This indicates that the operating system has registered a process that is actively waiting for incoming TCP connections on port 8080. In other words, the port is now in a listening state. This is exactly what happens when applications such as web servers, SSH servers, or database servers start up. They open a port and listen for incoming network requests. As long as the service is running, the port remains in the listening state and is ready to accept connections. Now that we have confirmed that port 8080 is listening, let's find out which application is actually using that port. For this, we will use the lswf command. Type sudo lswf-i :8080. Here, lswf stands for list open files. In Linux, network connections are treated as files, which means lswf can be used to identify the process associated with the network ports. The -i option tells lswf to display network related files and connections, while 8080 filters the output to show the information only for the port 8080. As we can see, the output displays the process that currently owns port 8080. In this case, it is the Python HTTP server that we started earlier. The output also shows useful information such as the process name, process ID, and the network address being used. This is a very useful technique when troubleshooting networking issues because it allows us to quickly determine which application is listening on a particular port. So far we have learned how to determine whether a port is open using Nmap, how to verify that a port is listening using ss command, and now how to identify the process that owns that port using lswf. Now let's visualize one of the most important concepts in networking, the source port and the destination port. To do this, we will use Wireshark, a network protocol analyzer that allows us to capture and inspect packet traveling across the network. First of all, make sure the Python web server is running on port 8080. Next, open a new terminal and start Wireshark by typing sudo wireshark. Once Wireshark opens, select the loopback interface allow. Since both the client and server are running on the same machine, all communication will pass through this interface. Now let's generate some network traffic. Open another terminal and type call http://127.0.0.1:8080. This command sends an HTTP request to our local web server. If we return to Wireshark, we can see that packets have been captured. To focus only the traffic related to web server, apply the following display filter: tcp.port == 8080. This will show only packets associated with port 8080. Now select the first TCP packet with the sync flag set. This packet is used to initiate a TCP connection. Expand the transmission control protocol section. Here, we can clearly see two important values, the source port and the destination port. The source port is a temporary port chosen by the operating system for this communication session. In this example, it is the port used by the call client. The destination port is 8080, which identifies the web server service that is listening for incoming connections. This demonstrates how port numbers are used in real network communication. The destination port tells the packet where it needs to go, while the source port allows the server to know where it should send the response. Every TCP connection, whether it's web browsing, email, file transfer, or remote access, uses source and destination ports in exactly the same way. Now let's understand the concept of port scanning. One question you might have is, how does a network administrator or an attacker know which services are running on a computer? The answer is simple. They don't guess. They perform a port scan. Before we start the demonstration, let's take a look at this diagram. At the top, we have Nmap, which is scanning our target system with the IP address 127.0.0.1. Nmap sends probe to multiple port numbers and waits for a response from each one. In this example, ports 8000, 8001 and 8002 are open because applications are actively listening on them. On the other hand, ports 8003, 8004 and 8005 are closed because no service is running on this port. Based on the responses it receives, Nmap can determine which ports are open and which are closed. Now let's see the process in action. First, we will scan a small range of ports from 8000 to 8005. Type Nmap-P 8000-8005 127.0.0.1. Here the -P option specifies the range of ports we want to scan. As we can see, all 6 ports are reported as closed. This is because no application is currently listening on any of these ports. Now let's open the first 3 ports by starting 3 web servers. In the first terminal, type python3-m http.server 8000. In the second terminal, type python3-m http.server 8001. And in the third terminal, type python3-m http.server 8002. At this point, 3 different applications are actively listening on ports 8000, 8001 and 8002. Now let's perform the scan again. Type Nmap-P 8000 to 8005 127.0.0.1. This time the results are different. Notice that ports 8000, 8001 and 8002 are now reported as open, while ports 8003, 8004 and 8005 remain closed. Why? Because only the first 3 ports have services listening for the incoming connections. This is exactly how port scanning works. Nmap checks each port individually and determines whether a service is available based on the response it receives. By analyzing these responses, administrator can discover running systems on a system, while security professionals can identify unnecessary or exposed services that may need attention. This simple demonstration shows how a port scanner builds a picture of the services running on a device without ever logging into the system. Now let's demonstrate one of the most important concepts in networking, that is port forwarding. Before we start the demo, let's take a look at this diagram. In this before section, a client attempts to connect to port 9000. However, no application is listening on that port, so the operating system refuses the connection. As a result, the client cannot receive any service through port 9000. In the after section, the situation changes. The client still sends traffic to port 9000, but the Linux kernel intercepts that traffic and forwards it to port 8080, where our Python web server is actually running. This process is known as port forwarding. The application itself never changes ports. Instead, the operating system rewrites the packet destination before delivering it to the application. Let's see how this works in practice. First, start a simple HTTP server on port 8080 by typing python3-m http.server 8080. This starts a Python web server and makes it listen on port 8080. At this point, nothing is listening on port 9000. Let's verify that. Open another terminal and run Nmap-P 9000 127.0.0.1. As we can see, Nmap reports that port 9000 is closed. This is expected because no service is currently listening on that port. Now let's create a port forwarding rule. Type the command as shown on the screen. Let's break this command down. -t-nat tells IP table to use the NAT table, which is responsible for modifying network addresses and ports. -a output appends a rule to the output chain. This means the rule applies to packets generated locally on this machine. -p TCP matches TCP traffic. -t port 9000 matches packets whose destination port is 9000. -a redirect tells IP table to redirect the packet. -2 ports 8080 changes the destination port to 8080. Now that the forwarding rule exists, let's scan port 9000 again. This time, Nmap reports that port 9000 is open. But notice something interesting. Our Python web server is still listening only on port 8080. We never started any application on port 9000. So why does Nmap see port 9000 as open? The reason is that the Linux kernel is intercepting packet destinations for the port 9000 and automatically rewriting their destination to port 8080. From the client's perspective, It appears as though a service is running on the port 9000, even though the application is actually listening on the port 880. Now let's visualize the forwarding rule. Type sudo iptables -t nat -l -n -b. Here we can see the NAT rule we created. The output shows that traffic destined for port 9000 is being redirected to port 8080. This confirms that the forwarding rule is active. So what is happening behind the scenes? When a client sends a packet to port 9000, the packet first reaches the Linux networking stack. The iptables NAT rule matches the packet. The kernel then rewrites the destination port from 9000 to 8080. Finally, the packet is delivered to the Python HTTP server listening on the port 8080. The server receives the packet as if it had originally been sent to port 8080. The client never sees this translation process because everything happens transparently inside the operating system. This demonstrates a very important concept. Port forwarding doesn't require moving an application to a different port. The application continues listening on its original port, in this case port 8080. Instead, the Linux kernel intercepts packets addressed to another port and rewrites their destination before delivering them to the application. This same mechanism is widely used by routers, firewalls, Docker containers, cloud platforms, and Linux server to redirect traffic between ports. And that's exactly how port forwarding works. And with that, you now understand one of the most important building blocks of computer networking, that is port numbers. Every website you visit, every message you send, every online game you play, and every server you connect to relies on ports working behind the scenes. Today, we didn't just learn the theory. We saw how ports open and close, how services listen for connections, how attackers and administrators discover service through port scanning, and how source and destination port identify communication endpoints, and how port forwarding transparently redirects traffic to the correct application. These are the concepts that every network engineer, system administrator, and cybersecurity professional must understand. But now that we know how devices find the right application, the next question is even more important. How does a connection actually begin? When you open a website, how do two devices agree to communicate? How is reliability established before any data is exchanged? That's exactly what we will explore in the next video as we dive into the TCP three-way handshake and analyze every packet step by step using Wireshark. If you found this video helpful, please like, share and subscribe to the Gaurab Tech. I will see you in the next one. Until then, enjoy networking.